Today we'll be having a conversation with John McCarthy, Professor Emeritus in the Computer Science Department at Stanford University. McCarthy received the Association for Computing Machinery's Turing Award in 1971 for his major contributions to the field of artificial intelligence. McCarthy coined the term artificial intelligence in his 1955 proposal for the 1956 Dartmouth Conference. He received his B.S. in mathematics from the California Institute of Technology in 1948 and his Ph.D. in mathematics from Princeton University in 1951. McCarthy is well known for his efforts to give computers common sense based on the use of mathematical logic and various extensions to it. He has made major contributions toward what he calls human-level artificial intelligence. McCarthy has also done extensive work in the mathematical theory of computation, especially proving the correctness of programs. He invented the Lisp programming language and made the key proposals and suggestions that led to time sharing. In addition to the Turing Award, McCarthy received the first Research Excellence Award of the International Joint Conference on Artificial Intelligence in 1985, the Kyoto Prize of the Inamori Foundation in 1988, the National Medal of Science in 1990, as well as several other honors. He's a member of the American Academy of Arts and Sciences, the National Academy of Engineering, and the National Academy of Sciences. Perhaps we can begin, John, by talking about what got you interested in science and mathematics in the first place.
Well, I was interested from the time I was a kid.
In high school?
No, even before that.
Even before high school. Somebody told me about a book called The 100,000 Whys. Is that something that had an influence?
Yeah, that was a Russian book. Because of my parents' radical associations, in fact, they were communists, these translations of Russian's children's things were popular, and 100,000 Whys is a pretty good book, a popular science book for children. And I read recently that it had been translated into Chinese, and some Chinese child prodigy had learned his science from that.
From that book. Is it still in print, do you think?
What?
Is it still in print?
Evidently.
Probably.
In China, at least.
In China, at least, if you read Chinese. Well, so then in high school, before high school and in high school, you had an interest in science, and then you went on to Caltech?
Yeah.
And majored in mathematics there. Any interesting stories about Caltech? No?
Well, there are, but I can't.
Well, you went to this symposium called the Hickson Symposium. You want to say something about that?
Yeah. This was right after I graduated from Caltech. I had some time out in the Army. But my first year of graduate work in math was at Caltech. I moved to Princeton second year. But anyway, in September of '48, there was this symposium on cerebral mechanisms and behavior. And it had various famous psychologists, including Carl Lashley and another one who'd worked with apes, whose name I'm forgetting now.
Kohler.
What?
Kohler?
Yeah, Wolfgang Kohler.
Wolfgang Kohler.
And they compared the computer and the brain. And many years later, when I got the Kyoto Prize, and they asked for a retrospective lecture, I went and looked at the proceedings of that symposium. And I had supposed that the that artificial intelligence had been discussed there, that is, the use of computers to behave intelligently, but at least there was no hint of it in the proceedings. But it was what gave me the idea.
So it played a role for you in getting you interested in the use of computers to imitate intelligence, even though at the symposium nothing much was said about that.
Me haggle about the word imitate. Using computers, making computers be intelligent, since we relate intelligence to the ability to do certain things, and independently of whether what does it is a human or a Martian or a mechanism.
Well, that brings us a little bit farther forward, but I remember you saying some things about being interested in the general science of intelligence, independently of how it's mechanized.
Yes, I can't say that I got very far with that.
There are certain principles about what it would mean for there to be a science of intelligence.
Yes.
Now, at Caltech, did you have any contact with computers? These were during the late 40s.
First of all, there was no computer there. The first computers were built in 48 and 49 in England and in the U.S. And I did attend a few lectures on programming for a computer that was not yet built.
And this would be
later contemplating, when I actually did learn to program in 1955, I could see that I had acquired some misconceptions in 1948. And if I had been given the opportunity to try to run my 1948 program, it wouldn't have worked.
Well, that kind of programming was what, all in machine language, right?
Yes, I think so.
Because it was certainly before any of the Fortran.
Oh, yeah, but before there were actual translators, people would write in a language that wasn't a machine language and then would hand translate it to machine language. The Russians had a big system for that.
And then, so after 1 year of graduate work at Caltech, you decided to go to Princeton. How come you just didn't decide to continue at Caltech?
Princeton was the best place for mathematics.
Let's see, there were various famous mathematicians there. Von Neumann, for example, but he was at the Institute.
That's correct.
And and then did you get to start working right away on a PhD research?
Yeah, when I arrived at Princeton in September of 49, the department chairman, Solomon Lefschetz, said to me, "What are you going to do your thesis on?" And I said, "I don't know, I'll think about it." And so I immediately got myself a notebook and started thinking about ideas for a thesis. And before the year was up, I had decided on a topic. And this made me relatively popular, because the usual thing is that the students pester the professors to suggest topics.
So you knew about your topic, but didn't have anything to do with computers?
That's correct.
It was...
In a vague sense, it did. In that I got interested in the notion of an integrating factor in differential equations. And the question that I asked myself is, what is an approximate integrating factor? And then what this led to was considering that the gradient of a solution to a differential equation, first order differential equation, belongs to two spaces. One is the space of gradients, and the other is the space of a vector satisfying certain algebraic equation. And that if one projected back and forth between those two spaces, according to a theorem of von Neumann, the process would converge to the gradient of a solution. That was my thesis, figuring out what those operators were. So in some principle, could have been a method for solving differential equations. But I couldn't, at that time, show anything about how fast it converged. It was maybe 30 years later before I was able to give an example and show that it converged very, very slowly.
So the problem stayed with you for those 30 years, and then you went back to it.
Yeah, thought about it from time to time.
Now you mentioned von Neumann in connection with doing a theorem that your idea made use of. You talked with von Neumann about all of this while you were there?
I only had one interview with von Neumann in which I told him some idea that I had about artificial intelligence, representing a brain and its environment by finite automata. And he encouraged me. He said, write it up. But afterwards, after my conversation with him, I came to the conclusion that it was in fact a bad idea because one couldn't represent knowledge in terms of the structure of the finite automaton, which was to represent the brain. So I didn't write it up.
So you wrote nothing?
Somebody else reinvented it and published it. And yes, it was a bad idea in his hands also.
It was a bad idea then, and still was. Huh?
Yep.
Yeah, well, it sounds vaguely like some of the things that Brooks did with his finite state machines controlling these little creatures.
I don't know about that.
Mm-hmm. So you didn't do anything then about artificial intelligence at Princeton except for that. And you stayed on after getting your PhD, you stayed on at Princeton for a while?
2 years as an instructor.
Mm-hmm. And now let's see. So then you had told me previously you spent some time at Bell Labs during a summer sometime around there?
Summer of '52, yeah.
And there you met Shannon?
Yep.
And you said that you, let's see, you and Shannon maybe collaborated on doing a volume of papers that you thought would be...
collecting a volume of papers, mm-hmm. Yes.
And that volume was Automata Studies?
Yeah.
But let's see, you said you weren't too happy about what all the papers that were submitted?
Well, I was hoping that people would write about artificial intelligence. And one or two did, but a number of them wrote just about automata. And the most famous initial paper on automata, which was Stephen Kleeni's, mm-hmm. appeared in that volume. Uh-huh. So I really didn't have any right to complain.
Mm-hmm. Had a famous paper in it. And but now the phrase artificial intelligence you had proposed later. What phrase were you using to describe your interest in those days in this field that would become artificial intelligence?
Now, I said I didn't have a phrase, but when I wanted to have this Dartmouth summer workshop, the idea was that people would come for the summer and work on artificial intelligence. I had to call it something. Mm-hmm. So I called it artificial intelligence. And I had a vague feeling that I'd heard the phrase before, but in all these years I have never been able to track it down.
Now, before the Dartmouth conference, you spent some time as an assistant professor at Stanford in mathematics?
Yep.
But anything going on with did you pursue any AI interests during those days?
Certainly I didn't write anything. I wrote on differential equations and analysis, and Stanford decided they'd keep 2 out of their 3 acting assistant professors, and I was the 3rd.
And so then Dartmouth was the winner on that one. Dartmouth got
Perhaps it won, or perhaps it lost.
So you went to Dartmouth as an assistant professor of mathematics, and it was there at Dartmouth that, was it you and Shannon, some others, decided to propose this Dartmouth Summer School?
Well, of course they didn't come up to Dartmouth. I went down to MIT, where Shannon had moved to. And the other person who was instrumental was Nathaniel Rochester of IBM, who was the head of their information processing department.
You had met him earlier?
I met him because IBM decided to give an IBM 704. And the idea was that it would be 1/3 to MIT, 1/3 to other New England colleges, and 1/3 IBM would keep for its own use. And I was the Dartmouth representative.
Part of the other New England colleges.
Yep.
And so that's how you met Rochester?
Well, he came up to Dartmouth as part of his tour, so to speak.
And so how did this idea about having this summer workshop, how did that originate?
Well, I'd heard about these Defense Department workshops. And so I thought that if one could get a lot of smart people, one could make substantial progress in a summer. It turned out to be very much over-optimistic.
So people came for various periods of time, right?
Yep.
Were all of them who participated ever there all at once?
Almost certainly not.
So they were there for certain periods of time. And what kinds of things did some of the people do there?
Well, do there is one thing, or report on is another. The people who were furthest ahead at that time were Newell and Simon, who came for just a few days. And I got the idea of list processing from them, but did not at all like the language that they used.
That was IPL?
That was IPL. I thought Fortran was much better. And now one of the things that was done there was that Minsky came up with the idea that a theorem-proving program should only try to prove things that were true in a model. And the example given was plane geometry. So you would have a diagram, and you would only try to prove things that were true in the diagram. And he wrote a little article about this, and Rochester decided that that was a good thing to do at IBM, and got a new PhD, Herbert Gelernter, to work on it, and had me as a consultant. And so I had these ideas about using Fortran for list processing, and Gelernter and his colleague Carl Gerbrich developed it further to this Fortran list processing language.
So they augmented Fortran with some list processing facilities?
No, they didn't do that.
They didn't do that.
What they did was they made some Fortran functions for list processing, but the overall structure was Fortran. And in 1958, when I spent a second summer at IBM, then I decided to write a program for differentiation, and it became clear that the natural way to write it involved recursion, and Fortran did not allow for that. So therefore, when I returned to MIT in fall of '58, it was clear to me that I needed a new programming language.
Well, there are two interesting things about that. One is the list processing. What was there about list processing that recommended it so for applications you wanted to pursue in artificial intelligence? What is there about lists that...
Well, you have data of variable size, and the key thing is that you can match the structure of the data by using lists. For example, a sum can be represented of plus followed by the summands. And so you immediately know that a list structure represents a sum without having to go parsing each time. And that has made for greater power.
And things that are a little more connected with artificial intelligence than arithmetic might be, I suppose representing, say, a theorem in geometry could be done as a list, or representing the axioms.
Well, more generally, any logical sentence also has a structure. It's a conjunction or disjunction or a universal quantification.
And then recursion. Why did you think recursion was going to be important?
Well, if you take the rule given in a calculus text as to how to do formal differentiation, then you have the rule that the derivative of a sum is the sum of the derivatives, which means that if you want to do the derivative and the expression turns out to be a sum, then you have to find the summands and call the a differentiation program on the summands. So that's where recursion
Naturally suggested itself. And now, in connection with the development of the Lisp programming language, was it the case you had earlier written a paper on computing with symbolic expressions? Did the paper come after Lisp, or did it precede Lisp?
Well, in the middle. Namely, we started on Lisp in the fall of '58. I had to write a quarterly progress report for the Research Laboratory of Electronics that would come out as a report in January of '59. And so I wrote about Lisp in that. And I wanted to show that you could have a universal function and that it was much more transparent in structure than a universal Turing machine. So I wrote out this eval function just as a kind of mathematical exercise, or to show mathematicians that Lisp was good for this purpose. Mathematicians paid no attention.
That was the germ of the paper?
But as one of the programmers, Steve Russell, did pay attention. He said, yes, if I program this eval in machine language, it will be an interpreter for Lisp.
There you had it.
I was a little skeptical of that, but he did it, and
so that was
fine.
the first. Was that the first instance of being able to run a Lisp program then?
Well, what we did is we were going to have a compiler, but the compiler was clearly going to take quite some time. So what we did is we had a bunch of conventions and hand compiled into symbolic assembly program.
Well, here we are at MIT, and you had been at Dartmouth. What was the transition? You could have stayed at Dartmouth, I suppose. How did it happen that you decided to go down to MIT?
Well, John Kemeny, who was the head of the math department at Dartmouth and who had hired me, arranged for me to get a Sloan Foundation fellowship, and I decided to take that fellowship at MIT. And then I double-crossed him by not returning to Dartmouth, but staying at MIT.
And that's when you met Marvin Minsky?
No.
No. Oh, you had met him at the workshop. That's right.
No, much earlier than that. Minsky and I were graduate students in math at Princeton at the same time.
He had done something on neural networks.
That's right. He'd built one at Harvard.
But you then had, of course, worked with him at Dartmouth Summer Conference, and then you actually got involved with an AI project at MIT once you ended up at MIT.
Well, we started the AI project at MIT. We met with, we had a conversation that decided that we'd like an AI project. And who should be coming down the hall but the head of, Jerry Wiesner, who was head of the Research Laboratory of Electronics. We said, we want an AI project. He said, what do you need? And I said, we need a room and a secretary and 2 programmers and a key punch. Mm-hmm. And he said, and how about 6 graduate students?
He had some that he could arrange for you to meet?
He had committed himself to support 6 graduate students in mathematics on a big grant that he'd agreed, big joint services contract. And he didn't know what he was going to do with those 6 graduate students.
You could unload them on you.
That's right.
Well, these 6 graduate students, they did then come and did they do some work on your AI project?
Yes, they did.
What sorts of programs did they write?
Well, a couple of them were working on the compiler for Lisp. Mm-hmm. I'm not exactly sure what the others did for us. Mm-hmm. They wrote their PhD theses in pure mathematical logic, mm-hmm. ignoring my ideas about proving programs correct. But then at least 2 of them later went into the field of proving programs correct.
You had mentioned one time to me in conversation about chess endgames. Was that one of those graduate students, or?
Oh yeah. Paul Abrahams wrote a program for 3-move mates and used my proposal for the Alpha-Beta Heuristic in that.
The Alpha-Beta Heuristic, which lots of people claim they invented.
Yeah. Well, Knuth wrote a big article about it, mm-hmm. in which he discussed who did what. And the complication was that there was a weak form of it and a strong form of it. And he was never able to establish who exactly did what. But both Arthur Samuel for his checker program and Newell and Simon for their chess program had some form of alpha-beta in it, and it may have been the strung form. And my original write-up on it, or well, maybe I wouldn't even say write-up, propaganda about it, had a complication to it where I considered optimistic and pessimistic evaluations.
Now, for people who are viewing this video who might not know what the alpha-beta heuristic is there a way to describe it in lay terms for what it is that it does?
Sure. If the simplest way to describe it would be to use the blackboard, but I don't suppose you want to do that.
So you'll have to speak visually.
All right. Here's the...
Or people could Google it, I suppose, and
I'm sure they could.
look it up on Wikipedia.
Yep. But the basic idea is this. Suppose I consider making a move, and then I consider that if I make this move, the opponent can capture my queen. Then I normally don't consider what else the opponent could do to me. Mm-hmm. Because capturing the queen is a disaster sufficient that I shouldn't make the move that leads up to it.
Whereas a more naive search process might look at all of these possible moves, right?
Well, the well-defined minimax procedure would indeed do that. Mm-hmm. And the minimax procedure was built into the first chess programs.
So as I mentioned in the introduction, you had lots of other interests, of course, besides artificial intelligence, theory of computation being one. You've already said something about that and the invention of Lisp. You also had these ideas about time sharing. Can you say something about how you decided to propose some ideas for that, for time sharing?
Well, for AI purposes, what one wants to be doing is to sitting in a terminal at the computer and interacting with your intelligent program so that you can see what it does and make it better. So given the expense of computers and also the fact that you spend most of your time sitting there thinking about what the computer has done, the obvious thing is time sharing, or at least it was obvious to me. So in '57, when I came to MIT on this fellowship, I proposed a simple form of it. But later it turned out that IBM, in connection with Boeing's desire to connect a wind tunnel to a computer, had invented or offered a system that had interrupts, which was clear to me that was really was going to work. That was what was really needed to be able to do time sharing. So we begged that from IBM and eventually got it, since MIT was in a position where it didn't pay for anything for that IBM 704. It begged, and it took IBM a little while before they decided, in fact, to give it to us.
And so then, after they gave it to you, then somebody implemented? You helped somebody implement an actual time-sharing system?
Yeah. It was complicated. An assistant professor by the name of Herbert Teeger was going to implement it, but his ideas got very elaborate. So the person who actually did implement it on the 704 was Fernando Corbato. And also, I was a consultant at Bolt, Beranek and Newman, and I talked to Ed Fredkin, who worked there, and I said, of course, the PDP-1 computer is too small. BBN was getting the very first PDP-1 computer, and he said, no, it's not. He devised what hardware mods would be required for the PDP-1 for time sharing, and persuaded his friend Ben Gurley, who was the chief engineer for digital, to put them in. And then Fredkin went off, and I was left with the time sharing project at BBN. Got somebody to program it.
On the PDP-1?
On the PDP-1. And it was ready in September of '62, which was the time when I left MIT to go to Stanford for the second time. And BBN didn't use it because there were so few users of the PDP-1 that it was still convenient to let somebody sign up for exclusive use of the machine.
Now, with regard to time sharing, of course, now computers are a lot less expensive and people can afford to have individual ones. And so, but still in all, even on these individual personal computers, there are versions of time sharing, right? In a sense?
What turns out, when personal computers were first invented, then people said, oh, we can get rid of this time sharing stuff. But then it turns out that if you want the computer to be printing at the same time you're doing something else or doing any other kind of task, you want time sharing anyway. So all of the basic software for time sharing is in modern operating systems, whether they be Microsoft or Apple, except that at least with regard to the Windows, these features were sort of dragged in and were not done very well.
Of course, with Apple, based on Unix, they were already there. Right?
Yeah, once Apple did base it on Unix.
Once they did it.
Yep.
And what about at MIT? So you were leaving MIT at about that time, but Corbato and others carried on with time sharing with, was it Multics? Did that get started?
Well, what happened was that one of the people who was at BBN was J.C.R. Licklider. And I got him enthusiastic about time sharing. And then he went to ARPA and undertook to have a time sharing project at MIT that he wanted me to be head of it. And he was a little bit surprised when he discovered that I had disappeared.
You were back at Stanford.
Yep. And
so he had to find somebody else.
Yep.
And was that Corbato or?
Well, MIT was rather hierarchical. Mm-hmm. So they put a professor of electrical engineering, Robert Fano, in charge, and Corbato under him, because Corbato was maybe just still an assistant professor or something like that. But it was Corbato who did the design and the actual work. Fano presided.
Anything else to say about MIT days before we move on to Stanford? You're leaving MIT, heading to Stanford.
Well, there was a big study that I ended up as, I wasn't the first chairman, but I ended up as chairman of it, that produced a report that said MIT's next computer should be time shared. Mm-hmm. And MIT I had made a big mistake. What I should have done was underestimated the cost of it. Instead, I was completely conservative and overestimated the cost of what it would be.
And that scared them?
That scared them into stalling.
I see.
So they wanted a market study. And I thought that a market study on the desirability of timesharing was like conducting a market study among ditch diggers as to whether steam shovels were a good idea. So when Forsyth at Stanford called me up and asked me to come to Stanford, I thought to turn him off by saying, I've been at Stanford before, I'd only come as a full professor. And he said, I think I can arrange that, which surprised me very much since MIT had just made me an associate professor.
So then we'll continue with Stanford days. So before we go on and talk a little bit about Stanford, let's conclude some of the discussion you had about timesharing. You had mentioned some things earlier about it.
Well, I've written up my recollections about it, and they're on my web pages, and also my January 1959 memo proposing it. But it got into the air, so to speak, very quickly, because basically speaking, the general idea can be expressed in just a few sentences. So the Dartmouth people got it from me, which they have acknowledged, and DEC got it from me, which they have acknowledged in this book by Alan Newell and maybe Gordon Bell, I think. But still nobody's written it up properly as to, talk to everybody who was involved and said who did what.
So there's an invitation. Somebody ought to go and look at that in a very scholarly way, see who did what.
I should have, unless too many of the people who were involved are no longer functional. But
Well, while we're on the subject of timesharing, apparently IBM, even though they provided the 704 that MIT used, they themselves didn't take to timesharing?
yes and no, or maybe one should say no and yes. Namely, the person who was in charge of IBM's next big computer, the 360, who was Gene Amdahl, decided that he didn't need to put any hardware into the 360 that was dedicated to timesharing. Now, MIT and IBM got into a dispute. And there were two aspects to this dispute. The first one was over money, namely whether IBM should pay MIT some large sum concerning the invention of core memory, which had been invented by J. Forrester at MIT. And that eventually got resolved after the heads of the two organizations resigned from each other's board of directors. The other was that after I left MIT, the committee that was in charge of timesharing came up with a very elaborate system involving pages and segments, which eventually led to multics, which was, and IBM would not make the modifications to the 360 that were required for this. And so Corbateau negotiated with General Electric, which would. And then at the last minute, IBM said, or somebody said to IBM, or Watson said actually, give them anything they want. And so IBM came up with this 360 Model 67, which did have all of that. But MIT had already decided to go with General Electric.
Who was making a computer at the time?
Yeah, General Electric was was a competitor in the large computer game. And but IBM did make this 360 Model 67, and did make their own time sharing system with it. But it was complicated and slow, in my opinion, because of the ideas that they took from the Multics proposal. Multics was never a success either. It had rings of protection and so forth, and it's had more elaborate protection than anyone has ever found it desirable to make sense.
Well, that's interesting that IBM was a little slow on that. And that was also the case, wasn't it, that even after Galerner did his work on geometry theorem proving, and maybe there's some other work in an AI, related to AI at IBM, IBM soon after lost interest in artificial intelligence?
It was more than losing interest. It was a development of actual hostility. There were two aspects of it. One aspect was a sort of sales aspect. I forget when, but maybe already as early as 55, IBM stopped using the word computer and talked about data processing machines, because these would be less frightening to their customer base. And then in 1959, somehow they decided that artificial intelligence was a bad idea and discontinued it.
So no more artificial intelligence work in the IBM laboratories until much later.
Yeah. IBM, artificial intelligence has had its ups and downs at IBM.
So now here we are at Stanford, and Forsyth was able to get a full professorship position for you at Stanford. This was in the math department at the time, was that right?
Well, the intention was to have a computer science department as soon as there were enough faculty. So it was a computer science division of the math department. So I came in the fall of '62. The computer science department was in fact established in February of '65.
65. And so what were some of the very early things you were doing at Stanford? You had a PDP-1 there, did you?
DEC gave me one. And then Suppies was interested in machine-aided instruction, and I convinced him that time sharing was the way to go. And he arranged for us to get a joint grant from NSF that allowed greatly beefing up that PDP-1.
And then you put a time-sharing system on it.
And then we developed a time-sharing system for it.
And then, so was there some early artificial intelligence work that you did on that system?
Well, yes. On game playing, we did a game of Kala. And we're able to establish that if they were started with 3 stones in each pit, it was a win for the first player. That is to prove that rigorously. We also, the programs indicated that it was a win for the first player with 4, 5, and 6, but we didn't have an actual proof of it. The PDP one was not powerful enough to do that.
Was there any work on chess at that time?
Not at Stanford.
Not at Stanford.
Or rather, actually, I started on a chess program when I was at MIT, and I taught the first course at MIT in programming for freshmen. And 3 of the people who finished that course took up my start of a chess program and wrote a chess program for the IBM computers in Fortran. And that was Alan Kotak's senior thesis. So he started out on it as a sophomore and finished it.
Now, your interest in artificial intelligence, of course, which got really going in pretty good shape along with the Dartmouth conference, you had written a paper which you gave in 1958 at Teddington.
Yeah,
can you
that
say a
was
little bit about
Programs
that?
with Common Sense. That was the first set of ideas that I had in which I retained confidence as that they were on the right track. As I told you, I didn't like the ideas that involving automata that I discussed with von Neumann. And in the automata studies, I had a paper, Inversion of Functions Defined by Turing Machines, which basically had the same defect. It didn't really permit direct representation of common sense information.
So you wanted to be able to represent common sense information in some kind of language which was declarative, and you had thought about the use of logic. So do you want to say a little bit more about those ideas? They were described in your 1958 paper, but have been ideas you've been pursuing ever since, actually, right?
Well, that's correct. Basically, mathematical logic as invented by, Frege, I would say, in 1879. Of course, the formal logic goes all the way back to Aristotle, but Frege's system was the first one that was sufficiently expressive. And that's good enough, in my opinion, for common sense. One needs some extensions for non-monotonic reasoning, and I think one also needs an extension for contexts as objects. But it's good enough. The logicians, however, have not been interested in pursuing common sense.
Now, that particular school of artificial intelligence, some have called it the logicist school, and there's been lots of controversy about it. I recently looked at an article again by Drew McDermott criticizing, even though he started out being interested in logic, criticizing the approach. So what
is that a recent article or his old article?
It was his old article. Anything to say about the pros and cons? I mean, some people say, well, look, humans aren't all that logical. A lot of what we do is not deduction, but something else. What would be your defense for logic against arguments of that sort?
Well, in the first place, that's right. A lot of the way people draw conclusions is not logical. But in the second place, people recognize the correctness of logical arguments. And quite apart from anything having to do with computers, if their arguments are incomplete as far as logic is concerned, people can be persuaded of that, or even that their arguments are wrong. So after all, logic was invented in terms of communication among humans, not specifically for the use of computers. Now, the people have had, from time to time, expectations of short-term success. And logic is one of those areas which has induced expectations of short-term success. Another one is neural nets and connectionism and so forth. And short-term success has eluded people. And so it looks like human-level artificial intelligence is quite likely to be a long-term proposition. At least it requires new ideas. And with regard to new ideas, you don't know when somebody's going to come up with it or not. Now, the current enthusiasm for short-term success is promoted by Ray Kurzweil. And I looked at, he wrote a book called The Singularity is Near, and I read his chapter on artificial intelligence. And as far as I'm concerned, he has not provided any sufficient basis for his short-term optimism. In fact, the chapter is not technical. It merely what it mainly consists of is reference to various demos.
So he's not pushing any particular point of view about what's going to lead to short-term success in artificial intelligence, right? He just says it's going to happen.
Yeah. And maybe it will and maybe it won't. But if it does, it won't be due to him.
He'll be there to help celebrate, he hopes, because he's also interested in extending his lifespan.
Yes.
Well, now, so somewhere around the time that Stanford decided to have a computer science department separate from mathematics, you helped start, or maybe did start, the Stanford Artificial Intelligence Laboratory under the acronym SAIL. Can you say anything a little bit about how that got started?
Well, when I came to Stanford and I asked Licklider for some money to do work on artificial intelligence, and he gave me a fairly moderate grant. Then I began to think about what was required for vision, computer vision. And the dominant idea at that time, which is still rather prominent, is making computer programs to do discrimination. For example, discrimination between the pictures of the letters of the alphabet.
Sometimes called pattern recognition or something like that.
Pattern recognition slogan is for something a little more systematic than that, I think. But the first things were using various ad hoc features. That is, does it have a hole in it? Well, that provides the beginning of a classification. Does it have something sticking down in it?
Selfridge was doing things like that, right?
I don't know whether he was or not. I wasn't thinking about him. But anyway, my idea was that you wanted description, not just discrimination. And my argument for that was that if you wanted to program a robot to pick up something, then it didn't just have to discriminate on the whole picture. It had to be able to locate the object and represent its shape. So I decided to try for robotics, and Licklider was gone by then, but I did apply and got a rather large grant or contract with DARPA to start the Stanford Artificial Intelligence Laboratory. In particular, the amount of money required for our very own PDP-6 computer that later got beefed up into a PDP-10 and then eventually to a KL-10 and so forth.
Did you get some students interested in doing this description work of scenes?
Yeah.
And also you had some faculty who were, additional faculty involved with artificial intelligence work there?
Yeah, Jerry Feldman, for example, who came as an assistant professor.
And then Les Ernest, who wasn't a faculty member but came to help run the lab?
Yeah, when I started running the lab, after a while I told Ivan Sutherland that I wanted to hire an executive officer. And he said, yes, you should. You're the only one of our contractors who has a perfect record. You have never submitted a quarterly progress report.
At all, or on time? Or
At all.
At all.
And he recommended Les.
Because he had known Les from Lincoln?
Yeah. And
then
Les took not only charge of that, but also was the substantial initiator of a number of the projects involving the time-shared applications of the computer, including PUB, which was the first really document-producing thing.
there are a lot of other things besides artificial intelligence that might be regarded, I guess, as scaffolding for all these projects, but PUB would be one, and with some other work also, right? Graphics?
Yeah, there were at least one thesis on graphics and
Displays, different kinds of displays.
Yeah. And control, that is controlling the cart. And the prominent, another assistant professor who had got his PhD at Stanford with me as his advisor was Raj Reddy. And eventually he disappeared, as many of our assistant professors did, when we were ready to renew their appointment as assistant professors. And
Raj
other
Reddy.
schools were willing to make them a higher position.
Whereas other schools wanted to get started in this field or expand in that field. Raj Reddy went to CMU.
That's right.
Eventually became a dean there. All right, well, but there was also music, work on the use of computers in music too, right?
Yeah, well, that was a sort of hanger-on. Namely, I let them use the computer, but no ARPA money was ever spent on them.
Having a good computer around attracts a lot of people who have ideas that they'd like to explore on a good-sized computer.
Well, that's right. I mean, for a while, besides the IBM installation, and some PDB-8 in various specific laboratories. We were the only general purpose computer on campus.
Mm-hmm. And Knuth used it also, didn't he, for his typesetting work?
That's right.
Mm-hmm. Well, now, besides the robotics work that was going on and all of these other things that were using the computers that you had, what sort of work were you doing, or what sort of thoughts did you have at that time that extended your use of logic as a representation language and moving toward representing the information needed for human-level artificial intelligence?
Well, I did improve my representations of common sense and wrote some papers. But basically, the problem of representing common sense knowledge, either in logic or some other way, is still unsolved, or at least incompletely solved, only partially solved.
Early attempts at the idea of implementing the ideas in your 1958 and other memos on the advice taker. There were some students who tried to implement some of those ideas.
Well, knowledge representation is a whole industry these days.
Mm-hmm. Well, I guess I was getting at people like Black.
Or has been for a long time, since the 70s.
Uh-huh. Well, I guess I was getting at people like Black and Cordell Green and their attempts to actually use the situation calculus that you proposed.
That's right. Well, that was 69, Cordell Green.
But these were early attempts, but not completely. They certainly were not, didn't lead to the success that Kurzweil would have liked.
That's true. And every now and then, somebody comes along and says, well, you see, this hasn't got us to human level intelligence, so my idea must be better. And then they make a lot of propaganda and get some money, and after a while, their idea doesn't lead to human level intelligence right away either.
Well, these various ideas that people have tried.
Connectionism is the example that I want to give.
Connectionism, subsumption, Brooks-Bayes networks.
Yes.
Well, nevertheless, do you think that the combination of these ideas might, in fact, be useful?
I don't know. I mean, I think logic is fundamental.
Now, in terms of extending logic, you're also well known for your work on circumscription, which is one way of achieving a non-monotonic logic. Do you want to say some things about that? Non-monotonic logic in general and circumscription in particular?
Well, first of all, one can observe that people do non-monotonic reasoning. That is, draw conclusions from partial facts that they might not draw or would not draw if there had certain additional facts that do not contradict the partial facts. And so, fact is, you have to draw conclusions from partial information. And some people have jumped to the conclusion, maybe 100 years ago, that was probabilistic, but it turns out that that's not the only way in which humans jump to conclusions. So circumscription is a formalization in mathematical logic of this property, and I wrote 2 papers on it.
So it essentially involves something like if well, there are various more simpler versions of non-monotonic reasoning than circumscription. There's, so for example, the default logics, and they're related to circumscription.
They overlap it. They're not simpler. The simple one is predicate completion, where you have some predicate and you say so-and-so implies this predicate, then you say so-and-so if and only if the predicate. That's predicate completion. And then there's negation as failure in prologue. That's simple in prologue, and it also existed in microplanar. Both of those date from the early 70s.
Isn't there a use also that the database people make, in which if some particular fact is not in the database, you can assume that it's not true?
Well, that's sort of commonly done. I don't know to what extent it's qualified. In other words, if you have a database of Stanford students and you look up a name and it's not in the database, then you conclude that this person is not a Stanford student. So you assume that the database is complete, which you might not always want to do. Now, as for circumscription, it's based on the idea of minimizing the extent of a predicate, allowing certain things to be varied in order to achieve this minimum. So in that respect, it's very analogous to minimization in mathematics generally.
What are some other things, because you have other ideas that you've suggested would be important to achieve human-level artificial intelligence? Non-monotonic reasoning is one, but you've also investigated some other elaborations of logic also, haven't you?
Some of them are elaborations of logic, or at least one major one is an elaboration of logic. Many of them are things formalized within logic. That it doesn't require any extension of the logic. For example, concepts as objects.
You reify the concept.
Yeah, and you can do that within logic. And I advocate such reification as a competitor to modal logic. Now, the thing that, as far as I can see, does require an extension is contexts as objects.
So, if you were to sort of summarize what you think a new graduate student working in artificial intelligence might want to work on, in addition to all of the different things that come up, like connectionism, Bayes networks, other neural network techniques, subsumption. What are some of the core, what do you think a person ought to set about that he could actually, or she, make progress on in, say, a dissertation?
Well, representing particular domains of common sense knowledge is, in my view, the thing that will really give us the clues as to where we need to go towards human-level artificial intelligence. That being more important than for the moment, than coming up with new general theories.
Well,
Now, there's some nice problems, like a person who has come up with a bunch of nice problems is Ernie Davis at NYU. And one can mention one of his, namely the birthday present problem. So A and B are thinking about a birthday present for C, and C must not know the birthday about what the present is in advance, and therefore A and B should not talk about it in the presence of C, and so forth. And to formalize all the necessary facts for that is something that I'm not sure whether there are any published attempts at that.
so formalizing a particular, more or less circumscribed problems in which common sense is needed would be a good idea.
Yeah.
How
But
many of those?
consider the general notion of secrecy. One would presume if you want to do this birthday present problem, then you ought to come up with some general notion of keeping something secret by, for example, not leaving the birthday present lying around, not talking about it, and so forth.
How many of these particular divisions do you think we would have to work on before making some progress toward general common sense? Are we talking about 6 of them, or 100 of them, or?
20. Needless to say, if you really had even 10, somebody looking at the 10 might get some way of saying, well, there really aren't 10 there are only 3, and putting it together.
Now, if you look at psych as one example of trying to represent common sense knowledge, do you think psych includes a lot of these?
Well, it includes a lot. I've asked people to do various things for me in psych, and it's never really worked out. I can describe one example, and that was arranging for a dinner. And psych was able to say that, well, you need a table and you need silverware, but it didn't come up with you need only one table, but you need silverware for each diner. This was quite some time ago, so maybe psych is better in that respect. But somehow its representation of requirements for some action at least how it's used has not been adequate.
Now, if you were to...
He's holding us up.
5 minutes.
Oh, that's fine.
Now, if you were to pursue that kind of work with psych, trying to get it to reason about various things, and made notes of its inadequacies, would that, do you think, be a good way to proceed? Because for every one of these inadequacies, I suppose you could add something to psych.
Yes, that's a good idea, provided you doesn't mean John McCarthy.
Well, would it be a good idea for students to do something like that, do you think?
The trouble with any specific project is who knows that the student might end up spending all his time on the politics of psych or on the sysadmin of psych. So the student would have to be, or his advisor would have to be capable of getting through those two things at least before the student would be really conceptualizing it.
Do you think that the effort that went into psych was worthwhile? That that's a sort of thing that makes progress toward human level AI?
Yeah, I think so.
If so, should there be more of them that would have perhaps somewhat different points of view about how to proceed, and therefore
yeah, certainly quite different point of view about how to proceed, except that I'm not sure what this different point of view is. But you know, Lennart made a real good try. I think more recently, in order to get support, he's undertaken to do whatever DARPA wants, and probably what DARPA wants is associated with various current slogans, which may not be the best path towards human level AI.
one thing we haven't touched on, and maybe we could do this sort of to conclude, is your views on progress in learning. It looks like machine learning is an important topic in AI these days, and lots of people are involved using it for one thing or another, and control and so on. How about learning? What do you have to say about learning?
Well, the stuff that I've read about learning has been mainly discrimination and not learning, well, maybe how to describe things. And the example that I'd want to give is learning new concepts like secrecy. But also, I have an example on my webpage about learning the three-dimensional reality behind a two-dimensional appearance. I have a little puzzle up there called, in my webpage, appearance.html that some people have played with. And the people who have done something serious with it are Stephen Muggleton and Ramon Otero, using inductive logic programming. But they haven't fully solved it yet.
Now, inductive logic programming is a variety of learning, isn't it, where one does more than just discrimination?
That's correct.
So there's a lot of possibility of learning statements there if one has what they call a bias or a...
Yeah, because I believe with inductive logic programming, you can learn something that has variables in it. At least free variables that are implicitly universally quantified. I don't know whether it goes up to learning the full predicate calculus sentences that can have alternations of quantifiers.
All right, well, that's interesting. Is there any further things you want to say in conclusion of the interview? To give cheer to people who are doing work in artificial intelligence? If the goal is not around the corner, is it? Are we making progress?
There's something I would want, if you can do it, to stuff it in the middle somewhere. And that is when you were asking about the virtues of logic. The things that the logicians have proved, for example, Gödel's completeness theorem, in which he showed that anything that is true in all models of a given collection of sentences is provable. That from the point of view of AI, that's important. Probably more important than his subsequent incompleteness theorem. Because nobody is expecting to make programs that can prove, that can decide arbitrary mathematical sentences.
So although it's important to be able to show that something true in all models is provable, the detractors of the use of logic would say, well, that may well be, but it might not be provable in practice.
Well, that's so, but in limited domains, you can deal directly with models. And in fact, the satisfaction programs do that for a limited part of logic, namely propositional logic. So
been quite successful.
I guess the point I wanted to make there is that for AI, logic is inevitable in the same sense that for physical systems, calculus is inevitable.
So
Stuff that in there somewhere.
we'll do that. So in conclusion, I think it's worth pointing out that McCarthy's websites have an awful lot of information. Pointers to papers, pointers to things like the original Dartmouth proposal, ideas that he's had on topics that might not have found their way into formal papers yet, plus a lot of information about some of John's opinions on matters outside of artificial intelligence. So highly recommended to visit. The URL would be something like JMC at somewhere.
No. You better write it down.
You could Google John McCarthy.
Yeah. Problem is that the general systematic way of handling the URLs of faculty members came along after my particular URL was established. But Googling John McCarthy will
We'll get you to
get you there.
everything. Okay, well, thank you very much, John.